Okay, now let's talk about a reaction that is really, really important both on the lab scale and on the industrial scale, and that's catalytic hydrogenation. So when we say hydrogenation, all we're saying is that we want to add hydrogen to something. I want to take some pi bond, usually unsaturation, and I want to add hydrogen to it to make a saturated compound, right? So I'm just adding hydrogen across this double bond, making two new CH bonds. So this is usually what's called heterogeneous catalysis, which is to say my catalyst is not just going to be acid or base, it's going to be some solid that is not going to dissolve in my pot, right? So it's going to be some basically brick dust that's going to stay there. And the important thing to remember about heterogeneous catalysis is that all of your reaction is going to be on the surface of your catalyst, okay? So if you're using some expensive metal catalyst, you don't just want a solid ball of metal, because you'll only get reaction on the outside of that ball, and you're going to be paying for the expensive stuff on the inside of the ball that's not doing any reaction. A good example of this is a catalytic converter in a car. If you've had a chance to look at a car's catalytic converter, it essentially looks like a brick, like literally a porous ceramic-y brick. And the reason they do that is because the surface is coated with some really expensive metals, right? The Park Place of the periodic table, your palladiums, your rhodiums, your platinums, all of that. And you can't afford to put a brick of platinum in your Chevy or your Corolla or whatever. And so you're going to just put a little bit on the surface of this brick and put all your exhaust through that. Okay. So there are a couple different ways to approach this problem. So there are two ways to approach this catalyst problem. I can get something that's cheap and difficult, title of my memoirs. Nickel, iron, those are plentiful metals that will do this reaction, but you'll need high temperature and pressure. How high? Maybe 50 to 250 atmospheres of hydrogen. You might remember that hydrogen is flammable. So high pressures of a very flammable gas is a challenging engineering problem. It's not an impossible engineering problem, but we will have to pay engineers to do it. There's also expensive and easy. So as I mentioned, the expensive part of the periodic table is your palladium, platinum, ruthenium, rhodium. We're going to almost always use palladium. And even then, like I said before, we're going to coat something with palladium. So we'll draw it like palladium on carbon, which is just carbon dust that is coated with palladium, maybe 5 to 10% by weight, right? So you'll just, again, it's a charcoal powder that with a little bit of palladium on the outside. So the great thing about this is that now we can just use 1 atmosphere of H2. So when I'm doing this in my lab, we just fill a balloon. We literally fill a balloon with hydrogen, and that balloon pressure is enough to make this go. Which of these are better? It's going to depend on what you're trying to do and the scale on which you're trying to do it. So in my lab, if I'm trying to make a gram of something that is pretty precious, I will always use palladium and gentle conditions, right? I might even use platinum or ruthenium if my palladium reaction doesn't work. But this is fine on a lab scale. But if I am on a plant scale, if I'm trying to hydrogenate vegetable oils to make margarine or something like that, I really cannot afford that much platinum, right? So there I'm going to have to, again, hire some engineers to set something up for me so I can use a cheap catalyst on scale, okay? And again, if I can figure out the palladium, I mentioned catalytic converters before, And I mentioned that every car in the world has one to take some of the more noxious elements out of your exhaust fumes, and that most catalytic converters have these really expensive metals in it. If one can design a better catalytic converter that uses the cheaper metals, that would have a huge impact on a lot of things. The cost of cars, maybe the environmental impact of cars. That would make somebody very rich and have a massive societal impact, right? An unsolved problem. Here's an example of a reaction that I might do in the lab. So here's an alkene. I'm going to give it some palladium on carbon. The exact percentage isn't always written down, but maybe it's 10 mole percent. Very small amount. Obviously, palladium is expensive, so I want to use as little as I can to make it work. Hydrogen, 1 atmosphere of hydrogen in a balloon is often going to be good enough. If I can go up to 10 to 15 atmospheres pretty simply with laboratory equipment, special laboratory equipment. And then I can do this at room temperature. And let's say ethanol, again, our solvent, if it's doing what we want, does not involve in the reaction. So don't be looking to force this to make a bond to solvent, because that doesn't work. Okay? So what am I going to see out of this? I'm going to see 2 different hydrogenated products. Again, I'm not going to change the stereochemistry here. Here are the products that I might expect to see. One thing I'll note is that my hydrogens are almost always, is very high percentage, going to be cis to each other. Why is that? Remember, this is a reaction on a surface, right? So I've got my surface of palladium here, and my molecule is going to have to sit a certain way on that surface, all right? And so as the molecule kind of docks onto the palladium surface, it's only natural that it's going to take hydrogens from the metal center onto the same face, right? There's no backside attack or anything like that happening, okay? So I'm almost always going to see them add to the same face. So does that mean that I'm going to get 50% this and 50% that because alkenes are flat and it's equally likely to attach on both sides? Well, yes or no, right? This isn't really flat. This part is flat, but I've got this isopropyl group over here. That's not flat, right? This is going to affect how it comes onto the ring, right? So if my isopropyl group is on this thing, it's probably more likely that this is going to complex the surface with the isopropyl group facing away from the surface, right? And so what does that mean for the hydrogens? It probably means the hydrogens are going to add to the opposite face. The important thing to remember is that my hydrogens are getting delivered cis to each other. How does catalytic hydrogenation work? What's the mechanism? Well, a metal is involved. So this is, strictly speaking, organometallic chemistry, which is a focus we'll spend a little time on next week. But for now, let's just say that the mechanism is not quite as easy and clean as the SN2 mechanism and such things. So I'm going to give you kind of the rough scheme of this. You won't need to actually do arrow pushing on your own for this. You won't need to know this mechanism. But here is an example of how this is important and affects you. This is oleic acid. It is the main component of olive oil. It melts at 14 degrees Celsius, which is too low for margarine, right? So the taste of this is okay. I don't want to spread this on my toast because it's already liquid and I would have to like put a knife inside oil and spread it. It's nasty. Maybe some people like that. I don't like that. I need something to look like butter, okay? So here's what we're going to do. I've drawn this as a palladium reaction, but it's probably going to be iron or nickel because, again, we're at the margarine plant now, right? We're at Blue Bunny or Kemp's or whatever, massive production facility. What's going to happen on the surface of these metals is that we're actually going to have hydrogen come in and be split onto the metal. So now I've got hydrogen atoms that are directly adsorbed onto this metal center. Okay, so the metal surface rather. So I've got kind of metal bonds or metal hydrogen bonds here. I'm going to undergo a process called oxidative insertion that I will cover in more detail next week. But long story short, I'm going to end up with one of those hydrogens transferred over to this carbon. So one of these hydrogens is here. And I'm still going to have this, it's going to happen sequentially. So first I'll get one hydrogen delivered to the carbon, and I'll still have this carbon metal bond. And then later on, this carbon metal bond will kind of rearrange with this hydrogen here, and I'll end up with my hydrogenated vegetable oil. So this is stearic acid. It melts at 69 degrees Celsius. So that's actually too high. So this is more like wax. This will not melt on my toast. This melts too low. This melts too high. Okay? So if I'm trying to get margarine, and I am, this is a big problem. So the solution to this is maybe kind of obvious. You run the reaction, picture a reaction in a big pot, and I'm doing my hydrogenation, I'm stirring it, and it's getting thicker and thicker, and eventually, sometime between 0% and 100% conversion, I'm going to get a melting point between these two numbers that I like. And then I'm going to stop there. All right? So when we talk about partially hydrogenated vegetable oil, that's what we're talking about. We ran this reaction for a while until we got some mix or some conversion to product that put the melting point where we wanted to. And once the melting point looked good, we colored it and shipped it out. Here's the problem with that approach. This reaction technically is reversible. All right? It's not reversible once I get to here, because here I've got no pi bond to grab the catalyst. But from here, technically this thing can eliminate backwards. We'll call that reductive elimination. And again, we'll talk about that more next week. But reductive elimination doesn't necessarily need to take the same hydrogen that it gave. Which is to say, reductive elimination doesn't need to give me the cis alkene. I could also eliminate to the trans alkene. And that's where trans fats comes from. If I don't run this reaction all the way, if I stop it halfway through, I'll see a byproduct that's a trans fat, not a cis fat. This comes from reversible reaction here. So this organometallic intermediate eliminating a different way. So the problem with trans fats isn't its melting point, although its melting point is probably, unsurprisingly, closer to stearic acid, right? Because it stacks better. Trans fat stacks better than cis fats. The problem is that this is actually a little bit toxic. This causes heart problems and so forth. So trans fat apparently gives us an elevated risk of heart disease. Right? Our bodies kind of can't deal with trans fats. So it's a simple solution, right? I need to carry this reaction all the way forward, right? Even if I have trans fats, if I hydrogenate them, everything ends up at the same product. And then once I have 100% conversion, I can add some oleic acid back in there to get the melting point that I want, right? So it's not really a deal breaker, but it does change how I manufacture this stuff. Anything that's partially hydrogenated, I'm going to worry about getting some trans fats as a byproduct of that reaction.